So welcome to the last class before fall break. I can't wait for fall break. Honestly, I can't wait for winter break. Anyway, I'm done with the semester. I don't know about you guys. We're going to be looking at regression and prediction. The two lectures next week are going to be by the redoubtable Prakarsh and Adnan. Prakarsh will be covering time series analysis, and Adnan will talk about compressive sensing. So I get 2 weeks off from being up here and talking. Today we're going to be talking about things that you're probably very familiar with: regression and prediction. Are you looking at the slides? Shut it down. Thank you. Right. So we'll be looking at nearest neighbor regression and classification. We'll look at linear regression. I have a little application. I don't know if the sound will play over here. I'm going to try. And its relation to nearest neighbor regression. We'll look at regression in kernel spaces and kernel regression, which are two very different things. And we'll look at regularization, right? So here's the problem. Here are the two problems of classification and regression. In classification, you're given a feature X. You have to determine the class Y. So you're given an image features. You have to classify if this is a face, right? Or if you're given regression, you'd be given an input X, but then you must be estimating another feature Y as opposed to a class. So you'd be given, for instance, age, height, and gender of a person, find out the weight. Now, these look like real different problems. One of them is finding categorical variables. The other is finding continuous valued variables. But really, at the end of it all, it's just estimating one variable from a bunch of other variables. They're all the same problem. So let's look at it from the trivialized point of view, right? You have seen one or more people who are exactly 160 centimeters, and they're exactly 50 kilograms, and they're all female, right? Now I give you a new instance of a person who also happens to be exactly 160 centimeters and exactly 50 kgs. What's your guess for the gender of this person? It's going to be female, right? Because this matches the example that you got. Or a regression problem. You've seen one or more people who are exactly 160 centimeters. They're female, and the weight is 50 kgs, right? And then I get a new instance of a person who's a 160 centimeter female person. What would you guess their weight to be? 50 kgs, right? Based on your example. But now, what if the weight of that test person is 49 kgs, right? There's nothing in your exemplars that's actually an example space which is actually going to be able to tell you anything about this person, right? Or if the height of the person were 159 centimeters as opposed to 160 centimeters, you're screwed. Now, what you are performing is example-based prediction, right? And what you're really looking at is nearest neighbor-based prediction. So for example, if I'm trying to guess the color attribute of a bunch of dots. So I'm given some examples. Some dots are red, some are green. They all live in two-dimensional space. And then I'm given this one gray dot. I ask you, what's your best guess for the color of this dot? What would your best guess be? You can just look at the nearest training instance. The nearest training instance is green. So you can say, based on what it's closest to, I can say the color is probably green. So there's an assumption I'm making over here. What is that assumption based on this? So the nearest neighbor? You're sort of assuming that the examples sort of give you a bound on some region of the space. And you can find which region of the space any particular test instance is based just on the one nearest example, right? Now, but that doesn't sound like enough, right? Can you trust only the nearest neighbor? What if the next nearest neighbor is almost as close, but a different color? Then what would you say, right? This is not going to be, now you can't be entirely sure. So we can step up. You can find the k closest training instances. This is the k nearest neighbor method. and predict the desired attribute based on these k closest neighbors. So here again, you have the problem of predicting the color of this gray dot. If you're looking at just the nearest neighbor, you're going to pick green. But suppose you look at the three nearest neighbors. The three nearest neighbors over here, two are red and one is green. And so if you're looking at the majority, you're going to say, this is probably red, right? Now, so this is your k nearest neighbor. This is the k nearest neighbor problem. You want to predict as the k nearest neighbor solution. In the simplest case, you're going to predict as the majority solution, majority opinion. But then simple majority doesn't make a lot of sense, right? You'd also ideally want to look at the actual distance. So over here, I have one green dot, two red dots. These are the three closest neighbors, but the red dots are somewhat more distant than the green dots, right? So once I begin considering the distance, how much importance does each of these neighbors have in making my prediction? Is something that's close just as important as something that's far away? Clearly not, right? Now, if I'm performing a numeric prediction, this is just for categories, green or red. If I'm performing numeric prediction, then how would I use the same principle? Obviously, the values of predicted value of all the nearest neighbors can be completely different. There's no notion of a majority. So the majority won't even apply, right? And so then you actually want to say that I'm going to assign an importance to every instance, all of the exemplars that I've got. And the importance I assign is going to depend on something, the distance of how far away that instance is from where I am. So let me look at the problem of classification. I'm going, for any given test instance, I'm going to assign some weight to all of the neighbors. And so this guy will have some weight. So let me call this W1. This has some weight W2. This has some weight W3. I look at the three nearest neighbors to find out, what is the dominant class in my neighborhood, and add the sums of the weights of all of these neighbors. So the score for red is going to be W1 plus W2. The score for green is going to be W3. You'd compare the two, you'd pick whichever was larger, whichever class had the larger weight. On the other hand, if you are performing prediction, you're not just counting categories, right? Then what you will actually do is a weighted average of the predicted value of all of the nearest terms, or a weighted sum. So I have three terms. This would be W1, this would be W2, this would be W3. And let's say I'm predicting, for instance, the height of a person, and the two axes are some other attribute, weight and whatever else, right? So now each of my neighbors is going to have a height value. That's my Y. And so the height predicted for this test instance is going to be W1 times Y1 plus W2 times Y2 plus W3 times Y3. So you'd go over the neighbors and perform a weighted sum of the predicted value of all of these neighbors. Now, what would the ideal weighting be? Something that's close must have a larger weight. Something that's far away must have a smaller weight, right? And so here are some typical weighting functions. If the gray is my test instance, I can just look at the distance, the Euclidean distance between my exemplar and my test instance. And the larger the distance, the smaller the weight must be. So I could just say, for instance, that the weight is 1 over d, right? Or it could be e raised to minus alpha d, where you get to choose alpha, meaning the weight falls off exponentially as you go far away. Or you can do something simpler. Instead of looking at distances, I can look at similarity, right? And what is a common notion of similarity? The dot product, the inner product. And so I can say that my weight now is going to be the similarity, right? Something that's more similar. Again, the inverse of distance is also just similarity, right? The further away it is, the less similar it is, the smaller the weight. So instead of just computing a distance and making the weight the inverse of the distance, I can just directly look at a similarity measure that we're all familiar with, which is the inner product. And so I can say the weight of this instance will simply be inner product of my test instance and the instance itself. Everybody with me so far? And so here's your first form. Okay. Is anybody done? This can't be so hard. Aman is done, right? Mel, what's the answer to the first question? True. And Ben, the answer to the second question, false, right? So KNN uses the labels of the nearest neighbor as defined under a distance measure to make prediction, right? The K closest data points to a given testing instance always have the same weight. The first one is true, and the second one is false, right? So let's continue. Now, here are the two classification rules that we got. I picked up my K nearest neighbors, and I assigned to every neighbor a weight. And the weight was basically a measure of how similar that instance was to my test instance. So you could do it in one of two ways. You could compute the distance and make the weight inversely proportional to the distance, or you could directly make the weight proportional to the similarity between the two instances, where the similarity is computed in terms of inner product, right? But then if you're actually assigning a weight to every instance, why restrict yourself to the K nearest instances? Wouldn't it be just simpler to consider the entire world? Because if things are very far away, the weight is going to be small. They're going to become irrelevant. And so you could just consider all of the training data, and presumably you get smoother, more robust estimates. And so you can just say, I'm going to assign, when I make my prediction, I'm going to consider every single training instance. Now, every single one of my exemplars is going to have a weight, where the weight is a function of my current instance and the exemplar. And when if I'm performing classification, I'd go over all of my training exemplars, and for each class, I'd add the sums of all of the training instances that belong to that class, and then pick the class for which the weight is largest. If I'm performing regression, then I'm just going to do a weighted sum of the predicted value of all of my exemplars, where the weight is just the nearest neighbor weight, right? Now I'm no longer restricting myself to the K nearest neighbors. It's generally exemplar-based prediction. I can still call this nearest neighbor prediction, right? Just for terminology. And once again, what are the weights, possibilities of weights? You can make the weight proportional to the inverse of the distance, inversely proportional to the distance, or you can just make the weight proportional to the similarity, which is once again your inner product. Everyone with me? Right? I'm going to be working off this last example. Remember this, because this is going to show up all over the world, not just in today's class, but everything you ever do in your life. Yes? Pardon me? Get to them in a minute, right? So you're just looking at angular similarity, something, and the length. You're given a bunch of examples. When you're close to something, things that are longer will end up having more importance. We'll see, right? So here's how we are going to be doing your classification, right? Nearest neighbor classification, you'd be summing the weights of all of the red instances here. You'd be summing the weights of all of the blue instances, where the weights for all of the instances are the inner product between your test instance and your exemplar, and pick the class by which the distance is largest, or the weight is largest. Or if you were performing regression, you'd just be doing a weighted sum of the y's for everything. Which brings us to this other problem. Does this actually make sense? Now, think about it, right? If I'm predicting height from weight, now if I'm predicting height from, say, weight and give me something else, the length of my hair, right? And if I'm using inches to measure the length of my hair, versus if I'm using centimeters to measure the length of my hair, should this make a difference to my prediction of the weight? No, right? The units should be irrelevant, should they not? So similarly, if I just take everybody's height and multiply it by a factor of 4, just because I'm using a different unit, this shouldn't make my prediction change. So in other words, simply scaling one of the variables should not change the prediction that you make. The predictions must be scaling invariant. That making sense to everybody? Right. How would you make the prediction scaling invariant? Normalize. Normalize how? Okay. Speak up. Subtract the mean. Is that scale invariant? Scale it by the square inverse of the standard deviation, right? That makes sense? So if I normalize everything, I can just say I'm going to subtract out the norm, make everything zero mean because the position should not matter, and then normalize the variance out. Then it won't matter what unit I'm using. It becomes scale invariant, right? So this is not how you're going to be doing your nearest neighbor prediction. This is how you're going to be doing your nearest neighbor prediction. What do? We're going to scale everything by the inverse of the covariance. So when you scale everything by the inverse of the covariance, you're basically making the variance 1. But if you have a multivariate feature vector, then what would you be scaling it by? You'll be scaling it by the inverse of the standard deviation, the square root of the covariance, right? So if you have a multivariate vector, you would be scaling it by the covariance matrix, the inverse of the square root of the covariance matrix, correct? Now, how would you compute the square root of the covariance matrix? I have my covariance matrix C, right? How am I going to compute the square root of the covariance matrix? Okay, speak up. How do I diagonalize it? Okay, go ahead, Alex. Okay, I can eigen decompose it. And is it going to be E inverse, or can I just write E transpose? This is what kind of matrix is a covariance matrix? Symmetric. What are the bases? What are the singular vector? What are the eigenvectors going to be? How are they going to be? Orthonormal. So what is the difference between the inverse and the transpose? Same. They are the same thing, correct? So now this I can write this as transpose, right? How do I take the square root of this? I can just take the diagonal matrix, which is my lambda, which is going to be, lambda 1, all of these are zeros, right? Lambda 2 and so on. So the square root of this is simply going to be the square root of these guys, right? Square root of this raised to minus half is going to be just raised to minus 1, right? Lambda raised to minus half is going to be square root raised to minus 1, right? Or I can write this as 1 over square root of lambda 1, all zeros, 1 over square root of lambda 2, and so on. And so square root of c inverse, or c raised to minus half, is simply going to be e times lambda raised to minus half times e transpose. Everybody with me? Yes. It's a symmetric matrix. It's always positive semi-definite, right? Make sense? Specifically, you want this to be positive definite because you cannot invert a zero. Okay, but once you do that, so what this means is that you cannot have any component with zero variance, because if that component has zero variance, that component is contributing nothing to your distance or similarity measure. It's useless, right? And so now I can just go from my x to my x hat, where my x hat is a standardized feature. And now I can compute my similarity based on my standardized feature, except that this standardization is going to apply to both my exemplars and my test instance. This covariance matrix would have been computed on the training data, on the exemplars, right? But then I'm going to apply to both my exemplars and my test instance. And now I can compute my similarity based on the standardized features and perform my regression, right? So what is this standardization doing? If you have a scatter of the kind that you have on the top, once you standardize it in this manner, the scatter is going to be perfectly circular, right? What was this process called? Whitening. So you whiten the data before you perform nearest neighbors. And then thereafter, all you do is compute your regression based on, compute your regression based as a weighted sum, where the weight is simply the inner product between your test instance and the exemplars after they have been standardized or whitened. Everybody with me? Remember this. This ghost is going to come back. Now, all right, Alex is done and Darine is done, so we're done, right? Is the first statement true? False. Second one? Third? Fourth? False, right? And so we have the situation where we all agree that the order of the distance amongst data points is not invariant to scaling the axis. If I scale the axis, what was closest and what was not closest can completely change, right? And on the other hand, we do agree that the inner product is a pretty good notion of similarity. So the inner product is a good measure of weight, as closer points have larger inner products. Once they are standardized, otherwise this becomes irrelevant, right? And whitening is an essential step for the KNN algorithm. Now, here is another thing that you have to keep in mind. There's a certain dependence. There's an implicit assumption that all of the data points have what? Bean mentioned this a little bit. What is that? That all of the data points have approximately the same length. Otherwise, I can just increase the length of a data point out to infinity. And although it's actually going away, its weight is going to increase, right? when I take the inner product. So under what condition can I make this assumption? Pardon me? It's invariant to scaling, but still, if I have my test instance very close to the center, then things that are at the boundary are going to have more influence than things that are at the center simply because they are longer, correct? And so there seems to be something broken over here, doesn't there? But I'm claiming that this is not going to hold, statistically speaking. Why is that? As you increase the dimensionality of a sphere, where does the mass lie? Near the center? Where does the bulk of the mass of a sphere lie? Center? Okay. Suppose I've got a single dot. This is a one-dimensional sphere, a zero-dimensional sphere. Where's the mass? Right at the center, at that dot, right? What is a two-dimensional? Just a line segment, right? Where is the mass? It's uniformly spread, okay? What's a two-dimensional circle? Circle. Where is the mass? The bulk of the mass is out here, correct? There's very little mass in the middle. If I go down to a three-dimensional sphere, where is the mass? As you keep increasing the dimensionality of the sphere and the air, after a while, the entire mass of the sphere lies on the skin. It's a shocking result, maybe, to some of you at least. But when I'm working on a 500-dimensional sphere, the skin is it. You don't even have to look inside, right? What this means is that if I take two random vectors in high-dimensional spaces, they're almost certainly going to be almost the same length. So the length, what? But that is the case, right? So that's what we are depending on. But makes sense to you guys? Manohar? I'm seeing a great look of great puzzlement on your face. No, it's not. Oh, that's just his natural look. So, okay, classification and regression, that should not be are two versions of the same problem. You are predicting an attribute of a data instance based on other attributes. Nearest neighbor prediction, predict the weighted average of the desired attribute from all of the training data. And the amazing fact they never told you is that every form of prediction, classification, or regression is just a variant of weighted nearest neighbor prediction. Okay, let's hold that up. We're going to change gears. Now, I like using these Rube Goldberg pictures. Let's look at linear regression. I changed topics. I went from nearest neighbor to linear regression. How many of you are familiar with the notion of linear regression? Everybody. Who is not? Are you familiar with linear regression? Raise your hand. Thank you. Right? So are you familiar? Okay. So here's a common problem. I'm going to actually use linear regression on this problem. I'm assuming that I can hear sounds. Please play. What happened? Did I kill everybody? Not yet. Got the glitches? Okay. This is a common problem. If you actually went to these old recordings, they were recorded in these vinyl recordings, and they weren't stored very well, right? They got damaged, you get these glitches, and you want to remove it. Turns out that, cleaning up these old music recordings and old audio recordings was a huge research problem for the longest time, because we had this vast treasure trove of audio recordings, but they all sounded like this. So how do you clean this up? First, we have two problems. We have to find out where the glitch is happening. Then we want to erase the glitch, because you don't want to be hearing the glitch. But is it enough to erase the glitch? No, then you're going to have holes. What do you need to do? You're going to fill the hole up, correct? So you want to clean out the glitch, and then you're going to have to fill up the hole. So how can you fill up the hole? You look around, you can predict it based on past values, right? Predict trends. If you look at the portion of the signal to the left of the hole, It's got some pattern. I can extend that pattern from left to right. I can look at the similar, and this is what I'd call forward prediction, right? Similarly, I can look at the portion to the right of the hole. I can extend it backwards. That's backward prediction. Either of the two would work, except that if you're just doing purely forward prediction, by the time you get to the right end, there's going to be a discontinuity. You would still hear the glitch. If you're simply doing a backward prediction, by the time you got to the beginning of the hole, you're going to hear a click. So you do it both ways and average the two, just to make sure that, with the weight going up to the middle and tapering off so that you get something smooth. But then how exactly do you do this prediction? So for this, we want to do regression analysis. But this is just about filling the hole, right? How exactly do you find which portions to erase? So you can actually do regression-based reconstruction anywhere, not just in holes. So at each point in the recording, I can try to predict that recording from what is to the right and what is to the left. And if there's a big gap between what I predict and what I see, then that's probably a glitch, right? If the error, the L2 error between what I predict and what I see is huge, I can just erase that portion. I can call it a glitch. So this is regression. You're trying to find a pattern, and then you're trying to make predictions based on what you've already seen. This is a general problem, right? You're analyzing relationships between variables. Here you're analyzing relationships between the values in the hole and the values before the hole. And this can be expressed in many forms. Here are all the various kinds of regressions that I found on Wikipedia. And at some point I ran out of screen space. Now, basically, it's a tool to predict variables. The standard mechanism is like this. You're going to assume you have some feature or some value x, based on which you're going to try to predict some value y. And you have a collection of data for which you have both x and y. You're going to make an assumption that y is some function of x. But when you make this assumption, the function is typically parametric. The parameters are shown by the value theta that follows the semicolon. For different values of theta, you're going to have different functions. So which theta would you choose? You would choose the theta for which the error was smallest. But is that optimal function ever going to make a perfect prediction? No. So you can say y equals f of x theta plus e, where e is the error. And you're going to try to estimate the theta such that this error e is smallest. F can be anything, right? Typically, we like linear functions, but they can be nonlinear functions. If you're using neural networks, it's a very nonlinear function. X can be anything. It can be a scalar, it can be a vector. Y can be anything. It can be a scalar or a vector. This is a generalized formalism. It's just regression, right? So f can be a linear or affine function, can be a nonlinear function. It can even be a time series predictor. So this is linear regression. In linear regression, I'm going to assume a linear relationship between x and y. So I'm going to assume that if I plotted the scatter of x and y, I can find a linear trend. And so then linear regression, if I'm trying to make predictions about y based on x, I'm going to call y the dependent variable. I'm going to call x the explanatory variable. And given x, you want to predict y as a function of x, and you're assuming that this relationship can be given by a line, as shown by the red curve, right? The red line. So this is just a linear regression. You can have any kinds of regression. I just like to put this up because this was some kid from Stanford who went on to become a faculty in Wisconsin. And here's how he fits a regression, right? This was his lab report. It went, check this shit out. That's a bona fide 100% real data, my friend. I took it myself over the course of 2 weeks. And this was not just a leisurely 2 weeks either. I busted my ass day and night in order to provide you with nothing but the best data possible. Now, let's look a bit more closely at this data, remembering that it's absolutely first rate. Do you see the exponential dependence? I sure do not. And then banking on my hopes that whoever grades this will just look at the pictures I drew an exponential through my noise. So I believe the apparent legitimacy is enhanced by the fact that I used a complicated computer program to make a fit. He actually put this on the web. Then he published this in the Journal of Irreproducible Results and became famous for it, but he's a legitimate scientist too. Anyways, the point is, you don't want to be fitting such regressions, right? Regressions must represent actual relationships between the explanatory and dependent variables. So let's go back to linear regression. Now, if I'm trying to define a linear relationship between a variable y and a variable x, I'm not really going to be defining a linear relationship. What sort of relationship will I have? What is the equation for a line? It's what? Somebody said that we'll use the A word. Affine, correct? So what is the relationship going to be over here? My predicted relationship, what will it be? Anybody want to help me? You're not supposed to look at the screen, right? Y equals, I'm going to say some AX. Is this my affine relationship? Then what do I need? Plus B, right? This is the assumption that I'm making. Is this going to be perfect? On my training data, is this going to be correct? No, right? What will be missing?
Error.
An error, right? And so this is your prediction. This is your error. And then how do you estimate the optimal predictor? You're going to try to minimize something there. What? L2 of what? What are you going to be minimizing the L2 of? Difference, so over there, what is it? The E, right? You're going to be trying to minimize you will try to minimize the expected value of E squared. This is your standard L2 minimization, right? And you're going to do this given a bunch of training data. So you'd be given a bunch of XY pairs. So I'd say Y1 equals 8. I'm assuming X is a vector. I'm assuming Y is a scalar, right? So I can say Y1 equals A transpose X1 plus B. Y2 equals A transpose X2 plus B. Y3 equals A transpose X3 plus B. But corresponding to each, there is an error, E1, E2, or E3. And you want to find the A and the B that minimize this error. How would I do this? Anybody? Least squares? Somebody mumbled something, which was the correct answer. Was that you? Least squares. I can put all of my y's in a row vector, correct? And then corresponding to each of the y's, there's an x. So I can put y1. So I have y1 equals A transpose x1 plus b plus e1, right? This is the error. So I can say y1 and equals, and then I can say x1 is my vector. I put my equals here. There's an A transpose, correct? And how do I deal with the plus b? I can add a 1 over here. I can put a b over here. And that's y1 equals A transpose x1 plus b, correct? Then similarly, I can write y2 equals A transpose x2 plus b, and so on. This making sense? And there's an error, but this is what you're trying to minimize. So if I represent all of this as a matrix Y, this is actually just a row vector Y, right? Then I'm going to say this equals A. So A is this combination of A transpose and B times X, where X is this guy, right? And what would I be minimizing the error between? Y and AX, right? What is the solution? What is the solution, guys? Thank you. Can everybody say this aloud again? Right, okay. So what is the solution for A? A equals Y times x pseudo inverse, correct? Everybody agree with me? Okay, beautiful. We've already solved this way back in the past, right? And so you're given some training data, you'll be given some training data instances, several xy. We typically define a divergence between the predicted y and the actual y that you observed. And you're trying to minimize the A to minimize this divergence. And the divergence that we like to choose is the L2 divergence, right? So what, again, just to remind you, what you're really doing is minimizing y minus the squared norm of y minus ax. And this, as we just saw, gives a pseudo inverse. But again, let's go back and see what we are trying to minimize, right? Let's try to plot this. If I plot this, then where's my chalk? If I plot this, we've seen a plot of this kind before, right? Where you have a bunch of x's and a bunch of training points. But then I'm trying to find a regression which predicts the relationship between x and y. So for this x, this would be the predicted y. So this is going to be the error, right? For this x, this is going to be the predicted y. That's going to be the error. For this x, this is going to be the predicted y. That's going to be the error. So in each case, you're measuring the square of the length of the perpendicular drop onto the line, and you're finding the line for which this error, square total error, is minimized. Right? And that's basically, so you've got to search through all the lines and find the line for which this error is minimized. And we know this, A equals y times pseudo inverse of x, right? Easy. Now, I'm going to write this formula out explicitly just for your reference. I have y, which is a long row vector, and equals A times, and x is typically going to be longer than its wide. You're going to have many more training data points than the dimensionality of the space, right? So when I have an x of this kind, I have x. What was the pseudo inverse of x? Anyone remember? Would x transpose be invertible? Okay. So I have x times x transpose, and then continue. This is going to be inverse, and then what happens? And then x transpose. Correct? This was your, was this x transpose? X transpose is on the left. Thank you. This was a pseudo inverse, correct? And so just using that formula over here, here's the pseudo inverse of x. And so A equals y times x transpose x transpose inverse. Everybody with me? Right? All right. Now, what if y is a vector? Nothing changes. Now if y is a vector, then on the left-hand side, these guys are vectors, correct? But then a vector is really just many individual components. And now A is going to be a matrix. A is no longer going to be just a vector. And so you're going to say y equals A times x. B will be a vector as well. The error is going to be a vector. But if you look at it, this is actually three joint scalar regressions. You're saying that the first component of y is a linear regression where the regression weights are the first row of the A matrix plus this B, which is the first entry of the B vector, plus error. The second component of y is a linear regression where the regression weights are the second row of the A matrix plus the second component of the B vector, plus the error, and so on, right? So basically, this is n separate single regressions. If I have an n-dimensional vector y being predicted on terms of a vector x, you can just call this n separate linear regressions, which are jointly estimated, right? So this is what we call multiple regression. You're regressing, you're predicting multiple values at the same time. Everyone with me, right? But I can still use the same math. I can put all of the y vectors into a big matrix Y. I can put all of the x's with the extension of a 1 into a matrix X, right? I can put the A matrix and the B vector side by side, and I'm just going to get y equals ax again as before, right? And once again, if I solve for y, you're going to end up with exactly the same equation. I'm going to say y equals ax implies, or let me say approximate, a equals y times pseudo inverse of x, which in turn is simply going to be x transpose times x transpose inverse. Everyone with me still? Okay, good. And so you can predict the y. You can learn the a. And then given a new data instance, you can predict the y, right? You're just going to take the x, you're going to multiply it by the a. You'd augment it with the extra 1 to account for any bias. You multiply it by the a, you get the predicted value of y, which is going to be correct on average, although not correct for every individual instance. So this is a simple solution, right? And so that's exactly what we're going to do for our problem. I'm going to predict using linear regression, except I'm going to make one small change. Every sample is going to be predicted on the basis of the previous k samples. So I'm going to say xt is a linear regression of the previous k samples when I'm going forward. And when I'm going backward, I'm going to say xt as a linear regression of the subsequent k samples. Everyone with me still? Right, okay. This is what we're going to call linear prediction, okay? And so if I'm writing out the forward regression, then I can look at a segment of data, segment of the signal, right? So let's say I have this entire signal. I'm going to be predicting that last sample based on the previous k sample. So I say xt is a linear combination of the previous k values. Then I go back one sample, and then I predict this guy on the basis of the k samples prior to it. So it's xt minus 1 as a linear combination of the k samples prior to it. And so I can walk my way back and predict each sample based on the previous k samples till I run out of samples, right? And so I can say xk plus 1 eventually is a linear combination of the first k samples. So all I've done is just basically written the same thing out in matrix form. What was just one continuous signal? By predicting each sample based on the previous k samples, I've converted it to a linear regression problem. Make sense to everybody, right? And now I can solve for the predictor A, which is simply going to be pseudo-inverse. The way I've written it, x equals capital X times A. The predictor came afterwards, right? So, but the pseudo-inverse rules still apply, okay? I can do the same thing, yes, Harry.
Instead, just accumulating data.
You're not accumulating the error. I'm just making that at each time. My predictor, instead of having XY pairs, the first k sample of form X, the k plus 1 sample forms Y.
Like we have a gap or hole of say.
We are not looking at the gaps. I'm just looking at a regular sample. I'm just building a predictor from a sequence where everything is known. Right? That makes sense? Okay. And I can do the same thing going backwards, right? I can predict every sample based on the k samples following it. So I can say x1 is a linear combination of x2 through xk plus 1. x2 is a linear combination of x3 to xk plus 2, and so on. And now I can write out the matrix equations, and I can compute my backward predictor. So now I know exactly how to estimate a linear predictor that can predict the next sample based on the previous case samples. And so over here, what I will do is to take a sliding window, and within the window, which is large enough, I'm going to build a linear predictor of some order, typically 10 to 15. And then I'm going to try to predict the next segment. So if the prediction error is large, then the next segment doesn't follow the same trend as the previous segment. I probably have a glitch. I can do the same thing going backwards. I can take a vote over the predictions of where the glitches are from both the forward and backward predictors and identify the locations of glitches. That makes sense, right? And that's going to find the glitches. I can erase the glitches. And then now I have my holes. I can use the same predictors at the beginning of I can use the segment of audio just before the beginning of a glitch hole. Build a predictor and fill in forwards. Then I can use the segment of audio immediately following the hole. Build a predictor and extend it backwards. Average the two. I've filled up the hole. Right? So how well does that work? Here's an example. This is an example where the blue line is the actual signal. We erased it. We estimated it using linear prediction, and the red line is the predicted signal. And you see there's basically no error at all, right? It's done a perfect job. And so let's go back and listen to what happens when we use this for actual glitch removal. And do this here. Fairly complex music, but it cleans it out, right? The power of linear regression. It's amazing, right? Something so simple, something so trivial, solves what seems to be a very challenging problem. Questions? Yeah.
These curves. Is there like any mathematical justification for that? Or?
Absolutely. Well, we won't get into it. But every time you use your cell phone, you're using linear prediction because that's how you encode the voice signals that go over your cell phone. Yes. I don't have, so even when I'm determining the hole, right? Now in the glitch, there is no predictability. So within the glitch, I'll find that the prediction error is horrible. So I know that it's a glitch. Even when I'm trying to learn the predictor, if I just look at the training error, if it's very large, then it's probably a glitch, right? So the point is, I can find the glitch. Once I find the glitch, I can just use the segment before the glitch to train my predictor. Yeah, and the section after the glitch for the backward prediction.
All the way down to X1 for the backward prediction.
You don't need to go all the way back to X1, right? We can just say, I'm going to use the last 20 milliseconds or 100 milliseconds. That's it. Yeah. Go ahead.
Is there any reason to make the backward rather than
The glitch is just going to be a big patch in the frequency domain, right? You'd be doing linear prediction across all frequencies. The idea remains the same. You just made the problem more complex. So anyway, so everybody understands what linear prediction is, right? But what are we really doing? So let me go back and let me write. I saw a beautiful colored looking chalk. No, this is not colored chalk. This is just, I have no idea what this is. Okay. Is there some chalk here? No, staples. I'm not entirely sure why a classroom needs staples and not chalk. Did I leave my chalk somewhere here? Does anybody see a chalk? There's one. Perfect. Okay. So we said, when we trained, we said y1, y2 equals, and then we said a times x1, x2, and so on, correct? And so we said a equals y times x pseudo inverse. Correct? Everybody with me? Which is the same as saying y times x transpose times x transpose inverse. That was the equation of the pseudo inverse, correct? So now let's see what this comes out to be. So now suppose I have my A. I have my A, which is given by this guy. I get a new instance X. How am I going to predict the Y? A times X, right? So this is going to be for any new X, Y hat equals A times X, which is going to be Y1, Y2. This is my training data times X1 transpose, X2 transpose, correct? Times XX transpose inverse times X. Does everybody agree that this is the case? Yes? Okay. Can I expand that out again? I can say that this is simply summation I, yi, right? xi times transpose times xx transpose inverse times x. Would you agree that this is the case? Because if I multiply this guy out, it's xx transpose times x, inverse times x. So that just becomes a single vector. The first vector times x times y1 plus the second vector times this guy times y2 plus the third vector, the third vector here times this guy times y3. So this becomes it. Everybody with me so far? Any questions? Okay, this is key. You're looking puzzled. On Zoom, any questions on what I did over here? Any questions, guys? Does anybody recognize this term here? What is that? Can I hear that loud? If the data are zero-centered, it is the covariance matrix, right? Within a scaling factor, but the scaling factor will go away. So I can write this as summation I, yi, xi transpose covariance inverse x, correct? Which is summation I, yi times xi covariance square root times covariance inverse times x. What is that? This is just whitening, right? What is linear regression? Linear regression is just nearest neighbors, right? If you whiten your data and then just do a straight up nearest neighbors, that's linear regression. Conversely, linear regression is nearest neighbors is linear regression is nearest neighbors. Everybody with me? So I promise that everything ends up looking the same, right? Here's your first instance. Questions? What happened? Why did things fly? So here, when I'm predicting a value, all that happened was y equals summation I, yi, xi transpose x hat. That's all that it became, right? Which is you whiten the data and perform weighted neighbors. And that's going to give you linear regression. So if I want to predict a new value, you're given a bunch of training instances. Y simply a weighted sum of the yi instances from the training data, where the weight of any yi is simply the inner product between the corresponding x and your test x after whitening, after centering and whitening, right? Beautiful. I don't know if you find it beautiful or not. I do. If you find it beautiful, raise your hands. Okay, thank you. So, okay, Alex is done. Is the first statement true, Aman? All right. Is the second statement true, Manohar? No. Guys on Zoom, is the third statement true? Is there anybody on Zoom? I'm guessing not. All right. So,
Yes.
true. Oh. And is the fourth statement true? False. Okay. Let's see how many of you are right and how many of you are wrong. The first three statements are true, right? Every form of prediction, classification, regression is just a variant of weighted nearest neighbors, weighted neighbors. We can regard classification as a special case of regression, where the scalar prediction is not a real regression, but a categorical value. And we will see later when I talk about SVMs that support vector machines are basically just weighted nearest neighbors with a categorical random variable, categorical variable. Shocking as that really sees. And besides pseudo inverse, we can also use maximum likelihood estimate to solve some linear regression problems. This is a trick question because there's a bunch of slides that you're expected to see in order to be able to answer that question. Anybody who answered true or false was just taking a guess. All right. So let me take a different perspective, right? When I said y equals x transpose xx transpose inverse, that assumed that made an assumption about x. What assumption did we make? That xx transpose was invertible. So what kind of matrix is X? It's going to be wide. You have more examples than dimensions. But what if I have fewer examples than dimensions? Then what? Is xx transpose going to be invertible? No, right? But I can still write y equals ax, right? And I can still write a equals y pseudo inverse of x. What changes? The formula for the pseudo inverse is going to change. The formula for the pseudo inverse is now going to get xx transpose inverse in the beginning and x transpose at the end. Correct? So when the number of exemplars is fewer than the dimensionality of the data, the previous explanation no longer holds, correct? But this is still nearest neighbors. How? So what I can do is I define something called a gram matrix. A gram matrix is a matrix of inner products. If I have my collection of training data, I can just compute the inner products of all of my training instances. That's my x transpose x. And so I can write my nearest neighbor prediction in terms of predicting based on y times G inverse, where G is the gram matrix, and the whole thing still holds. So, but now this means that you can't just use the y values directly. You have to sort of rescale the y values based on the similarity between the training data instances itself, because you don't have enough training data. You don't have enough training data to get a direct relationship between y and x. But once you do this, the entire thing still holds. So I can just write, some y triple dot equals yg inverse, and the whole thing still holds. Okay. Now I'm going somewhere with this. Where do you think I'm going? What was the key point over here? Why did we, what was the situation where we used this approach? The dimensionality of the data was greater than the number of training samples. Give me a situation where that can happen. Mm-hmm. Right, okay, so this is just the simple approach, right? The approach itself. This is linear regression in high dimensional spaces. Regression in kernel spaces. Your relationships may not be linear, correct? How do you convert non-linear functions to linear functions? We saw this in the last class. What did we do? You transfer it into a higher dimensional space where now the patterns become linear. And so I can just say that if I have a relationship such as this is clearly not linear, but I can assume that there is some high dimensional space where this becomes linear, and we've seen situations where this is indeed true, right? So what I will do is to convert everything to this high dimensional transform, push it into the high dimensional space, and now I can just use linear regression in the high dimensional space. Everybody with me still? Okay, but do I need to go to the high dimensional space? Why not? Because everything is based on inner products, right? The prediction for a new data instance is y times the inverse of the gram matrix in the high dimensional space times the inner product between my training data and the test instance also in the high dimensional space. You with me? Right? And of course, I can write the gram matrix like so. And so I can write my gram matrix as a matrix of inner products in high dimensional space. I can define my y triple dot as y times the inverse of the gram matrix. And the actual prediction is going to be the weighted sum of these y triple dot values, right? Except, of course, I don't need to go into the high dimensional space. I can just use a kernel function to compute the inner product. And so now I get this lovely relationship where I can get the modified y, which is simply y times the inverse of the gram matrix, where the gram matrix is computed entirely from kernel functions. And the weighting of any training instance is also computed using a kernel function. And now I'm performing linear regression to predict non-linearly related variables by moving them into a high dimensional space, but without ever explicitly doing so. Everyone with me? Guys on Zoom?
Yes.
I don't know if you find this beautiful or not, but there's nothing, we have not done any magic. Zero magic, right? This is just one step after the other after the other. But if you follow the thread, you end up in some very strange places. Now, okay. The first statement, true or false? Second, false, right? Thank you. Right? We can carry out nonlinear regression by applying a kernel function to linear regression, and the gram matrix will always be full rank. No, it's not true, because if all of my training data are identical, there's nothing to invert. So, great. That's called regression in kernel spaces, but there's also something called kernel regression, which is something entirely different. And that has to do with looking locally, right? So what we did in this class was we started off at a point, then we expanded out to the k nearest neighbors, then we went from the k nearest neighbors to the entire training set. And then we took the training set up into a high dimensional space and performed linear regressions everywhere, and they all ended up becoming weighted averages, right? But then I'm going to come back and go back to the beginning of class where I'm looking at small localized regions. And when we do that, that's what you call kernel regressions. So you learn a regression for any given data point, you're still going to be learning a linear regression. Again, keep in mind that a weighted regression is just a linear regression, right? Except that for any given data point, I'm just going to be looking at a small ball of instances around that data point to learn the regression and then perform a regression based on that. And because you're always performing local regression, the actual function that you learn can end up being very curved. So in this case, you're going to, for any instance x, you're going to be looking at a neighborhood of x, like so. And within the neighborhood, you perform a weighted average or weighted sum of all of the y values. Okay? And now the question is, if I'm looking at just a neighborhood, what is the weight? And when I'm looking at neighborhoods, then I have a little more. Firstly, if I'm looking at neighborhoods, the number of data points I'm going to see in this neighborhood is often very small. The entire business of whitening will no longer hold because my covariance matrix is not going to be very robustly estimated, right? So we're going to have to use other kinds of heuristics. And so what is W? For linear regression, you would use a inner product. But then for this to be scale invariant, you need to whiten it. And that's not going to be a very reasonable thing to be doing in local neighborhoods. So we choose some other kind of weights, where the property the weight has is that it falls off rapidly with distance. And you have different kinds of weight functions, which are just any function which falls off rapidly with distance. And then your predicted y is simply going to be an affine combination of all the instances in the neighborhood, where the affine weights are the normalized kernel terms, right? And typical kernels are Gaussians, Laplacians, density functions, anywhere. And as it turns out, this kernel regression, where you're just looking at a weighted sum of immediate neighbors within some ball, where you can define the density or the radius of the ball, and the weights are normalized kernel functions. That actually computes the maximum a posteriori estimate of y given x. And this leads us to the business of maximum a posteriori estimates of y. Look at the slides, right? I'm just going to move on to the last topic, which is regularization, which is again important. Now, the fact is, in all of the prediction that we did, we were using an L2 error. The problem with L2 error is that it is very, very sensitive to outliers. Yes. Was there a question? Yeah. So what happens? You're squaring the errors, right? So now, if I just have one data instance lying out here, a noisy data point, because the error is the square of the mismatch, that one guy is going to have an extremely undue weight when you're computing the regression. And so it's going to pull that entire line down, way out of whack. You would have been much happier just ignoring that one guy because you're actually more correct, right? So the L2 error tends to be highly sensitive to errors, but then to outliers. But then you have this issue. How do you identify outliers? Your definition of outlier itself is fuzzy because it's going to depend on the regression you find. Is this guy the outlier, or is the entire bunch of the things above the outlier? You don't know. So you start off with a more general principle, right? we have this issue. Least square fit is sensitive. The error is squared. So small variations in data can result in large variations in the weight. Outliers affected adversely. So it's unstable. It's also unstable. If the dimensionality of X is large, and if the dimensionality of X is larger than the number of training instances, for instance, the covariance matrix is not even invertible, right? So I can start off with a conservative solution. I can say that my standard linear regression, which is an exact fit to training data, is too sensitive. I don't want to do this, right? It's assuming a strong dependence between X and Y. What is the other extreme? No dependence between X and Y. X does not predict Y, correct? So the alternate assumption is going to be X does not depend on Y. But that's useless. So where you want to be is somewhere in between. It's a compromise between being extremely conservative and being entirely dependent on the data. And so you want to have large, you want to say Y is weakly related to X. And you're going to, your a priori assumption is that Y is weakly related to X. And you won't actually change this assumption till you see a very large amount of data. And so your initial assumption is that large increments in X will result in small increments in Y, but you're willing to change your opinion if you see a large number of instances where a large increment in X resulted in a large change in Y. And seeing just a few instances will not satisfy us. So that means over here, just adding this one guy, this is just one instance, right? An assumption of that kind should make you robust to outliers of this kind. So here's the believer's linear regression. You see two data points. You say, this tells me the entire story. My regression goes through these 2 points, right? Here's the atheist linear regression. It says X has no relationship to Y, right? And here's the agnostic. You're going to say, okay, I've seen a data point. I'm not going to say there's any linear trend, but the default is perhaps closer to what I've seen than 0, right? Then I see 2 data points. Now the believer, of course, is going to just, the believer in this case is just going to draw a horizontal line straight through the dot. And the atheist has the blue line, the agnostic is the red. And now once I see 2 dots, these are going to be their respective beliefs, right? The true believer believes that red line is the case. The atheist believes the blue line is the case, but the agnostic is somewhere in between. We want to be the one in the middle, right? So the data provide evidence, but the belief in the default is very strong. Now, what does this mean? By saying that the belief in the default is very strong, you want to say that the slope of your line must always be as small as possible, right? You want to say A is small. You want to say the amount by which you bias the function curve is small. Yeah.
What is the static meaning of being small for A and B?
It means the slope is small, basically. That's it, right? That the offset of, so by the default, it goes through the origin and the slope is 0. If B is small, the place at which, it's like, imagine you take a plane, you're allowing yourself to do that.
Yeah. How does it be related to this, robust overfitting?
So you're literally stating that having a large change in X doesn't have a large change in my parameter, result in a large change in my parameter unless I see it many, many times. That is how it's related, right?
Some special cases won't make a lot of change.
Yes, a special case will not make a lot of change. Right? Make sense? Okay. And so here's what we're going to do. I'm not just going to minimize my error. I'm also going to try to keep my parameters small. I'm going to say minimize my error and simultaneously make my A's and lambda small. I'll go over a couple of minutes, guys. Just what is A's and B small? And the way I do it is through this parameter lambda, which I can set externally. And now again, so ignoring the bias because that I can extend x by 1, right? And so I can just say minimize the error between y and ax while keeping the Frobenius norm of a small, meaning the sum of all of the squares of all of the components of a to be small, right? And lambda gives a measure of insistence that a must be small. It's externally set. And the conventional solution, if you didn't have that lambda term, is that you're going to be getting the pseudo inverse, right? Y equals x hat times the x hat over here is the one that's augmented with 1. So this first term is just your standard pseudo inverse. Now I'm doing something else. I'm also simultaneously trying to minimize this guy. So when I take the derivative and solve for it, because we've run out of time, I won't actually do it. The solution doesn't change very much. What happened over here? You multiplied x hat by the inverse of the covariance matrix, right? What is going to happen now is that you're just going to add a small lambda term to all the diagonal elements of the covariance matrix. There's a term for this. Ever heard of diagonal loading? When you add a constant to all the diagonals of a matrix, you're basically improving the condition number of the matrix and you're making it more invertible. It's a standard engineering trick. When you get a matrix that you must invert and you find you're not able to invert it, just add a small constant to all the diagonal terms. If you haven't done this at any point in your life, you haven't coded algebra, right? Now, if you wonder where that came from, that's just a ridge regression. We are saying that if I think of this as a regression parameter, this is exactly the equivalent of adding a small constant to all the diagonal elements of my covariance matrix before inverting it. And then I get my linear regression. And so the difference between being a true believer and an agnostic is just a small diagonal loading, which is pretty amazing if you think about it, right? So there are other forms of regularization, L1 regularization, and so on, lasso. I'll skip these guys, but I'm going to stop right here. This is wrong. We will speak about classification with linear models 3 weeks from now. The next week is off. And the week after that has our own dear Adnan and Prakash covering for you guys. Any questions? Thank you, everybody. Thanks for staying with me.